Welcome to the lesson on Central Limit Theorem. We're going to start off talking about sampling distributions and estimators, and then that's going to lead us into our discussion on the Central Limit Theorem, which is the main objective of this lesson. The Central Limit Theorem is one of the building block ideas of statistics, so this is another one of those things that you really want to make sure that you fully understand and grasp the idea of it, the concept of it, because it's going to help you understand why and how we can do confidence intervals and hypothesis testing and all the important inferential statistics that make up the vast majority of a statistics course. Okay, so let's start off by talking about what a sampling distribution actually is. A sampling distribution of a specific statistic, right, is basically just sampling over and over again of the same size. So you're going to take the same size sample, size n, right, samples of the same size, are taken from a population. And then you're going to generate a statistic from each of those samples, whether it's a mean or a proportion or a standard deviation, right? You're going to calculate one of our descriptive statistics from that sample. What the sampling distribution does is it represents the frequency or the probability of getting a sample of size n with any particular resulting statistic. So let's say we're doing this for the means, and we take a sample of size 100 from a population. We calculate the mean of that sample. We put all those data values back. We take another sample of 100. We calculate its mean. We do that over and over and over and over and over again. And so now we have 1,000 means. Let's say we did it 1,000 times. If we then did a frequency histogram of the means and put a nice curve on it, you would get a Bell distribution. And so this height here would represent how many times you got a mean of this value, and this height here would represent how many times you got a mean of that value, and so on and so forth. The beautiful thing about the central limit theorem is that this one here, x1, which is going to be the average of this distribution, right? Because when we have a normal distribution, the average is right in the middle. So the average of our averages, right? Because we took a bunch of means, so this is the average mean that we got from our samples. This will be the exact same mean as the population that these samples came from. But for now, all we're talking about is the fact that we can build a sampling distribution of a statistic. Just like we can have a distribution of just numbers, right? We can have just a distribution of numbers, and those numbers can have a normal distribution. We've seen examples where heights of adult males are normally distributed, or bone density, right, measures were normally distributed. All these different examples of a set of data that has a normal distribution. Well, now you're taking that kind of grandfather set of data, that population, you're taking a sample of it, and the sample has to be a certain size, and it's very important. These have to be simple random samples, right? So we have to make sure that we're sampling properly. So we take a simple random sample of size n, we calculate a certain statistic, whether it's a mean, a proportion, a standard deviation, a variance. We can even do it with medians and other things. So let's say we're going to do standard deviations, just so it's different from the mean. Calculate a standard deviation, write that number down, put the data back, take another sample, calculate the standard deviation. Of course, it's got to be another simple random sample. It's got to be the same size, right? Calculated standard deviation, put them back, do it again, put them back, do it again, put them back. Now you've got a collection of 100 or 1,000 or how many times you did it, standard deviations. And so now it's like you've got an entire new set of data. And that set of data will always have a normal distribution, even if the population that you took the data from, right, the one you took the sample from and calculated the standard deviation, even if that grandfather population doesn't have a normal distribution, all of the samples, when you calculate the statistic, those results will always have a normal distribution. So we can create a normal distribution from something that doesn't have a normal distribution. One of the more common uses for this is doing it on the mean. So the sampling distribution of the sample mean is just the shape of the distribution that you get when you are sampling from a population and calculating the mean each time. And as I said previously, this will always, right, always result in a perfectly normal curve, regardless of the shape of the population it comes from. We could have a population that is uniform distribution or skewed or irregular or whatever it happens to be, but when you sample over and over and over again and calculate a mean each time and now have a collection of means, right, that collection will always have a normal distribution. And as I mentioned, the sample mean will target the value of the population mean. So here's a visual. Regardless of what we start with, so these things at the top, these are the parent population that we started with. So if we started with a population that had a normal distribution, whether it was severely skewed, uniform, just all over the place, irregular, whatever it happens to be, the red lines here represent the averages, right? These are the means of each of these distributions. So normal, right in the middle, skewed, it's pulled a little bit to the right, uniform, right in the middle, irregular, it just happens to be somewhere, right? You have to calculate it. But as you sample, now this n equals 3, that means each sample you took was of size 3. And this means each sample you took was of size 5. It doesn't mean you took 5 samples. These graphs represent probably sampling at least 40 or 50 more times. Normally we sample at least 30 to 40 to get that normal curve out of our distribution. I have no idea how big this was. They didn't give me the details, but I would assume it's at least 30 or 40 samples, each of size 3, right? Each of size 10, each of size 20. And you'll notice that in all of those, the mean is exactly the same and it lines up perfectly with the mean of its parent distribution. You'll also notice that the curves are all normal. And as the sample size goes up, what do you notice about the shapes of the curves? And hopefully you're noticing that they get narrower, which means your standard deviation of each of these curves is smaller. So as your sample size goes up, the standard deviation goes down. And we actually have a beautiful, nice, perfect formula to tell us what that relationship is between sample size and standard deviation in regards to the standard deviation of the parent population. So everything is related very nicely. Sampling distribution of the variance, right? So now we're talking about variances instead of means, but it's the same idea. We're still going to take a sample of size n, calculate the variance, put those points back, take another sample of size n, calculate the variance, put them back, and do it over and over and over and over and over again. And regardless of what the original function looks like, we will always get a normal curve. So these are just some pictures that describe what a variance distribution will look like. They're always a little skewed. Sample variances target the value of the population variance. So just like the mean, the mean of the sample variances, right? So if we take the average sample variance that we calculated, that value will be the same thing as the variance of the population it came from. And then, as I said before, the distribution of the sample variances tends to be a distribution skewed to the right. So when we do means, we get nice, pretty, perfect, normal curves, but when we do variances, we get these things that are skewed. Okay? But we still get the result of the average of our distribution is going to be the same thing as the target statistic. In this case, it's the variance, right? Because we're taking data and calculating variances. So the average variance will actually be the variance of the population. So here is a slide showing the results from an online applet that will create samples from populations. The first half, the upper half, I set it up to have a population that was bell-shaped. right? And then I asked it to take samples of size 100, and then I wanted to take 1,000 of those samples. Ignore this. I wanted it to run variances, but it seems to default only to sample means, as you can see here, right? Sample means. So this graph here represents the distribution, right? The distribution graph of all 1,000, right? N equals 1,000 means. So it takes a sample of size 100 from this population, calculates a mean, and then saves that data value. Goes and takes another sample of size 100, calculates that mean, saves that data value. Does that over and over again, you end up having 1,000 data values. And if you graph those 1,000 data values with frequencies, this is your little frequency histogram, right? That's how many you have of each. Then it calculates the mean, the median, and the standard deviation of those 1,000 pieces of data. And look what you get. You get a mean and a median that are almost identical to the mean and the median. And then you get a standard deviation that's way off. But that's because there's an actual formula. The standard deviation, and we'll see this formula later, the standard deviation of your sample distribution always equals the standard deviation of your population divided by the square root of your sample size. And since I did a sample size of 100, the square root of 100 is 10. So if I take this standard deviation, right, the sigma of our population, divide by 10, I would get 0.82, and woohoo, pretty darn close, right? So that's our sample sigma, standard deviation. I tried it again with a skewed set of data, pretty severely skewed. Same parameters, sample size of 100 to make the math easy. Do it 1,000 times. And now it has the sample means, a set of sample means. And this must be a typo or some sort of glitch, because if it did 1,000 times, there should be 1,000 pieces of data, not 1,100. Here's the mean and median. Again, very similar, right? The mean especially. Median's off by a little bit, but that's because this distribution ends up being normal, so your median ends up being almost identical to your mean. But in this situation, when you have something that is skewed, the median is always off from the mean. You can see them right here listed in red and green. So that's why that one's going to be off, right? It targets the mean, it doesn't target the median. Okay, and then the standard deviation once again seems way off, but with the same formula we know that if we just take the standard deviation of the population and divide by 10, that's what we should get, and it's pretty darn close again. So we can target the mean and the standard deviation very easily with our sampling distributions. A sampling distribution of the proportion is the same thing that we've already seen. It's another sampling distribution, but instead of calculating the mean each time, or instead of calculating the variance each time, we're now going to calculate the proportion of our data. And that would just be when we have kind of yes-no or dichotomous data, so we can't really calculate a mean, so instead we have to calculate the proportion of our sample that were yeses, or the proportion, you know, that had a certain quality. We need to be very careful when we're dealing with proportional data, because we've seen p's before for probability and stuff like that. Just know that when you normally see a p in statistics, it's most likely talking about proportions, because we don't do a lot of work with probabilities. So the p by itself, and sometimes it's a capital P, but usually it's still lowercase kind of script italicized p. That's the p of the population. That's the population proportion. It's kind of similar to mu, right, is the population mean, and x bar is the sample mean. Well, p is the population proportion, and then p hat is a little like upside down v, that's called p hat. That's our sample proportion. And just like means and variances, the sample proportions target the value of the population proportion. So if we did the same thing, took a bunch of samples, each time we took the sample we calculated the proportion of that sample that, let's say, had blue eyes, wrote that proportion down, did that over and over and over again, then took the average of all of those proportions, that result would be the proportion of our population that has blue eyes. It's a beautiful thing. Sample means, variances, and proportions, as we've said, they target the population. So we call those unbiased estimators because they actually give you the right answer. They target them. They're unbiased. So those are the ones that we tend to use the most when we're trying to do inferential statistics. Means, variances, and proportions. Medians, ranges, and standard deviations are biased estimators. That means that if we were to do this sampling distribution, the result we got for the median, the range, and the standard deviation would not actually target the population median, range, and standard deviation. Medians are really bad. As you saw from our previous example, they can be off by a lot. Ranges can also be off by a whole heck of a lot. I mean, just look at some of these examples. Look at the range of the black population at the top, even though it's normal. Look at how wide that is from 0 to 50. And then look at what we get from our samples. You know, it looks like that's between 20 and 30 at most. Much smaller range. So ranges are horribly bad. Standard deviations are off by a little bit, but only a little bit. And because their bias is very small, we still tend to estimate population standard deviations based on sample standard deviations. And since the variances target perfectly, we can always just take the square root of that and we're pretty much spot on. Okay, here's an example. Consider rolling a die 5 times. Find the average, variance, and proportion of odd numbers of your results. Now, what do we know about the behavior of all sample means that are generated if we were to do this over and over again? We know that the mean of our sample will always target the thing that we're measuring. So here's a picture. We roll this die 5 times, and then we calculate its mean. That means just literally counting up the numbers on those 5 rolls and then taking the average of those 5 numbers. And so here in our example, we got a 3.4, we got a 4.4, we got a 2.8, blah, 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 blah. Then the histogram on the right is a frequency histogram of how many times we got each average. It's kind of blurry, but you can see at the bottom the 1.6 up to 5.6, right? Those are our averages of a roll of 5. And then how many times we got them, taller in the middle, smaller on the outsides. Because all of our outcomes are equally likely, we know that the population mean is 3.5. That's simply just taking a probability distribution, right, of x and its probability of 1 and 1/6, 2 and 1/6, dot, 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 right? If we a 6-sided die is a random variable of values 1 through 6, each has a 1/6 probability, and then if you sum up your x times p of x, that gives you your expected value, and in this case that expected value is 3.5. If you don't believe me, do the math and you'll see it. The mean of the 10,000 trials that this computer software ran for us got 3.49, which is pretty darn close. And the idea is if we continued it indefinitely, right, instead of just doing 10,000 trials, we did an infinitely many number of trials, then the mean of our samples would end up being perfectly 3.5. And then also notice that our distribution of our samples is normal, even though the distribution of the parent population is uniformly distributed. Right? This is a uniform distribution because each one of them has a 1/6 probability. Now if we talk about the second part of it, the variances. Again, all outcomes are equally likely, so the population variance is 2.9. That comes from our formula for doing variances of a binomial distribution, and we get 2.9. The mean of the 10,000 trials is 2.88. Again, very close, but if we did it indefinitely, it would hit 2.9 exactly. you'll also notice that this distribution is skewed, right? When we do a sample distribution of variances, we always get skewed, and it's always skewed to the right because variances are always positive. Remember, a variance is something squared, right? Variance is s squared, and if you square something, it's always positive. So our variances are always going to be 0 and above. You'll notice down here there's 0, right? So it starts at 0 and goes above, and it's always skewed off to the right because it couldn't be skewed to the left or it would go into the negatives. We can also do our 10,000 trials and calculate proportions. And again, since we have a uniform distribution and all outcomes are equally likely, we know that the proportion of odd numbers should be exactly 50-50 because there's exactly 3 odd numbers on a 6-sided die and 3 even numbers on a 6-sided die. And the proportion of our 10,000 trials ends up being exactly 0.5. That was just lucky happenstance. The idea is, though, that if we did it forever, it would exactly be 0.5, and you'll notice that this distribution is also nice and normal. Okay, why do we sample with replacement? Well, because sampling without replacement would be easier, right? It would avoid duplicating things, i.e., taking the same data value more than once. But if we're interested in getting these distributions right, we have to sample with replacement because we have to maintain probabilities. So if we're selecting a very small sample from a very large population, sampling without replacement makes no real significant difference on those probabilities. So we can technically fudge the numbers and not worry about it. Sampling with replacement also results in independent events so that those probabilities are maintained. So that's really why we want to sample with replacement. But as it says, if our sample is small enough in relation to the population it comes from, we can sample without replacement and not have to worry about it. Most of the methods that we're going to deal with in statistics require that our sample be a simple random sample. So just keep that in mind. If you're actually doing a voluntary response sample, i.e. you're taking surveys, or some sort of convenience sample, then the results you get could very well be extremely different from what you think. So you always have to report those results with kind of an asterisk and say, well, this is what we think the population looks like, but we could be very, very wrong because our sample was not a simple random sample. Now that we understand what a regular sampling distribution looks like and how it behaves, let's talk about the central limit theorem. The real reason why we started with all this stuff is to understand the central limit theorem. Okay? This tells us, the central limit tells us that for any population with any distribution, so it doesn't matter what our parent population looks like, whether it's a normal distribution, skewed, uniform, irregular, whatever it happens to be, we know that if we sample from it over and over and over again, the distribution of those sample means always approaches a normal distribution as the sample size increases. And in fact, usually once our sample gets above about 30, then we're going to get a pretty perfect normal curve. Given a random variable x with a distribution, which may or may not be normal, and that random variable has a mean and a standard deviation, go and take some simple random samples, all of the same size, selected from that population, and remember they have to be simple random. Then that's how and when the central limit theorem applies, right? So those are kind of the criterion that have to be taken into consideration when we try this. And if we do that, we know that the distribution of the sample mean will always approach a normal distribution. We know that the mean of the sample means is going to match up with the population mean perfectly, and we know the standard deviation of all the sample means is going to be the standard deviation of the population divided by the square root of n, which means if we know what our sample mean is, we can solve backwards, right? Because if this equals the standard deviation of our sample, all we have to do is multiply both sides by square root of n, right? Take our sample standard deviation, multiply it by the square root of n, and now all of a sudden that's the standard deviation of our population. So we can always figure out what the standard deviation of our population was based on that. Now this description is always talking about the mean of our sample. Means is the population mean, but remember this idea also works if we calculated proportions each time, and then the mean of the proportions would target the population proportion, and if we calculated variances each time, the mean of the variances would target the variance of the population. Practical rules commonly used is just, and I've said this a couple times, anytime the samples that you're pulling out, right, those sample sizes, as long as you're sampling more than 30 at a time, then your sample distribution tends to be very, very close to a normal distribution. Anything 30 or larger, you get a really good looking normal curve. If it's smaller than 30, and sometimes we can't take samples bigger than 30 because we don't have a large enough population to deal with, then we know that our sample distribution might not be perfectly normal, but it should be pretty close. If, however, the original population that we're dealing with is already normally distributed, then any sample size we pull from it will create a perfectly normal distribution, right? So if we're pulling from a normal population, then our sample distribution will always be normal, even if our sample size is less than 30. Some notation: when you see mu underscore x bar, that just means the averages of the averages, right? X bars being the things that you're calculating. So that's the average of your samples, and then the mu on the right, that's just your normal mu of the population. And then we've already seen that sigma x bar, right, that's the standard deviation of the means that we get from our sample, and that's going to be the standard deviation of the population divided by the square root of n, and this is also often called the standard error of the mean. Instead of standard deviation, standard error. Some examples: we start with a normal distribution, and we look at what happens when we take samples of size 1, 10, and 50. So even when we take samples of size 1, we get a distribution that looks fairly normal, and then 10 looks even better, and then 50, I know it doesn't look that great, but that's pretty darn normal. And so they all looked good because we started with a normal distribution. Now if we started with something that had a uniform distribution, like rolling a six-sided die, you can see that when our sample size is small, we don't get something that's normal. We get a uniform. And then when it's 10, it's getting a little bit better, but it's still not very normal. And there's all sorts of peaks and valleys in there. But once we get that large sample size of 50, we get that beautiful normal curve again. How about a U-shaped distribution? So our parent population that we're pulling from looks, something like this. Sometimes called a dumbbell curve or bimodal. Just got a U shape to it. If we sampled from that over and over and over again, well, if our samples were small, size 1, we get something that looks similar to its U shape. Once our samples start to get bigger, we get something more and more normal until it's perfectly normal, right? Am I beating this dead horse enough for you guys? Here's some more examples of, samples of 20, 50, 100, and 500. You can see that they get more and more normal as your samples get larger. So let's beat this dead horse one last time. As the sample size increases, the sampling distribution of sample means approaches a normal distribution. Here's an example. Suppose an elevator has a maximum capacity of 16 passengers with a total weight of 2,500 pounds. You guys have all seen these signs. It always says how many people are allowed in there, and it also has a total weight allowance. So let's assume a worst case scenario in which the passengers are all adult males, because we're going to make the assumption that an adult male on average weighs more than an adult female. We have to make another assumption. Assume adult male weights follow a normal distribution with a mean of 182.9 pounds and a standard deviation of 40.8 pounds. Pretty big assumption to make, but actually if you look at the way weights are distributed, they are actually fairly normal. Two questions. We want to find the probability that one randomly selected male has a weight greater than 156.25 pounds, and B, find the probability that a sample of 16 males have a mean weight greater than 156.25. So that B situation is, what's the probability that if 16 men all got on the elevator at once, that the average weight of those 16 males would be 156.25 or more, right? Because 156.25 times 16 gives you a total weight of 2,500 pounds. So we're basically just asking the question, if 16 men got on the elevator, what's the probability that their combined weight is over the limit of 2,500 pounds? Okay? Part A goes back to our previous examples of just dealing with a normal curve and using our z-scores and standardizing things that way, or we could use technology, right? We're basically asking, if this is my curve and this is my x that they give me, 156.25, how much area, right, is in the green bit? How much area is over there? And that tells me the probability that somebody is over 156.25. So you can use the z-score formula, or you can use technology. In either case, you get a probability of basically 74%. Part B, find the probability that a sample of 16 males, right, that their average is over that. Well, now we're dealing with averages. We're dealing with a sample. So that means we're back to our idea of a sample distribution. We know that if we take a sample of size 16 over and over and over again from a population that has an average of 156.25, right? Sorry, 182.9 and 40.8 was our standard deviation. Then we calculate a normal curve based on that distribution. So here's the picture that they draw. You don't have to make yours accurate as far as it doesn't have to be really thin and tall. Just draw a normal curve. You know that the average is the average of the population, right? So it's 182.9. Now the standard deviation of the population was 40.8. But our standard deviation, right, according to the formula, is going to be that divided by the square root of 16, which gives us 10.2. So now we have a new normal curve where the average is 182.9 and our standard deviation is 10.2. And so the question is, what's the probability that somebody is 156 or above? Well, 156 is over here, right? It's to the left of the mean. So we're looking for all of this stuff. 156.25. So ask yourself, is the answer going to be greater than 50 or less than 50%? And you say, well, it's going to be greater than 50% according to the picture. They're doing it with z-scores. I would recommend doing it with technology. But in either case, you end up getting 99.55%. This amount here, scribbled in, I'll do it in red, the red bit here, ends up being 99.56%. 99.55. 0.9955, which gives you 99.55, rounds up. What does that mean? Well, that means that if 16 men got on the elevator all at once, you're almost guaranteed that you're over capacity. Right? There's a 99.55% chance that that group of 16 men weighs more than 2,500 pounds, because there's a 99.55% chance that the average weight of the group is above 156.25. You know, some of them might weigh more, some of them might weigh less, but you're almost guaranteed that the average weight of each of them is above 156.25, so their cumulative weight is almost guaranteed to be above 2,500 pounds, and your elevator goes crashing to the floor and everybody dies. Yay, statistics, right? They always love to have these wonderfully morbid examples, but you get the idea. The last thing to talk about, and it's a very small thing that we probably won't use very often, so you can, for the most part, probably ignore this, is that whenever you're sampling without replacement and the sample size is greater than 5% of the finite population size, right? So remember before we said we can only sample without replacement if our sample size is really small relative to the population size. Let's say our sample size is greater than 5% of the population size, but we still want to sample without replacement. Maybe it's just because it's too tedious or too unlikely or too impossible to sample with replacement. If we're doing that, then we have to make this adjustment. We have to adjust for this sampling without replacement, and it's called the finite population correction factor. Who the hell cares what it's called, really? But there it is. It's a very simple number, right? Capital N is the size of your population, little n size of your sample, so it's really easy to calculate, but you only need to use it whenever you have this case. Your sample is more than 5% of your population size, and you're going to sample without replacement. So whenever that happens, you just have to use that correction. And that's it. That's the central limit theorem.